Welcome to This Explainer. Today, we're diving straight into the invisible world that actually powers our daily digital lives. We're going to peel back the screen, so to speak, to see exactly how the operating system acts as the ultimate hotel manager for your computer's limited hardware. We'll be looking at a top-level overview of OS support, focusing really heavily on how your device handles its most precious and, honestly, its most highly contested resource, memory. So let's just get right into this. Have you ever actually stopped to wonder how you can keep, say, 50 browser tabs open, stream a movie in the background, and maybe even run a massive video game all at the exact same time, even if your laptop only has 8 gigabytes of physical RAM? I mean, it kind of feels like magic, right? But it's actually this incredible feat of logistical engineering. The source text we're exploring today breaks down exactly how this brilliant illusion of infinite memory is maintained. To solve that mystery, we first have to establish what an OS actually does. At its core, an operating system is basically just a program that manages computer resources. It acts as a constant mediator, and it has two main objectives: balancing your convenience as a user against the absolutely ruthless efficiency required by finite hardware. The OS masks all those super complex hardware details from the programmer and from you, providing a clean, easy interface while doing some seriously heavy lifting behind the scenes.
Okay, moving into Section 1, the puzzle of partitioning, or as we like to call it, managing the hotel.
Let's take a look at how early computers tried to fit software guests into our very limited memory hotel. Early operating systems used what's called fixed-size partitioning. As we can see illustrated here, the memory is chopped up into rigid, predetermined blocks. Now you can probably guess the problem with this. If a 3 megabyte program goes into a 4 megabyte partition, well, a whole megabyte of memory is just sitting there entirely unused inside that block. It's totally trapped. Over time, all those wasted internal megabytes add up, which drastically limits how much the computer can actually get done. So engineers naturally tried to fix this waste by using variable size partitions instead, giving processes exactly the room they needed and not a byte more. But watch what happens as we move through this sequence. As programs open, finish up, and then close, they leave behind these tiny, unusable little holes of memory just scattered everywhere. And this headache is what we call fragmentation. The crucial takeaway here is that both of these early methods ultimately failed at true efficiency. Fixed partitioning wasted space inside the blocks, and variable partitioning created fragmented holes between the blocks. In fact, to fix variable partitioning, the OS frequently had to just pause everything and perform a compaction procedure. It literally had to physically shift active processes around in memory just to squish all the free space together into one usable chunk. As you can imagine, this was incredibly time-consuming and wasted precious processor time. Which brings us to Section 2, paging, a much-needed uniform solution.
The really elegant fix to this whole fragmentation nightmare was a brilliant paradigm shift in computer architecture known as paging. Instead of trying to manage varying sizes of programs or unpredictable memory blocks, paging just standardizes the whole shebang. It chops the physical memory into small, completely uniform blocks called frames, and then it chops the software processes into matching pieces called pages. Because they're exactly the same size, any page of a program can effortlessly slot right into any available free frame in memory. It's honestly a lot like playing with identical Lego bricks.
Now, to make this actually work, the processor uses a logical address, which is what the programmer sees, and translates it. The OS maintains a page table for each active process. Think of this table as a massive directory that maps a program's logical page directly to its physical frame in memory. This drastically reduces all that wasted space we talked about, because at the very worst, only a tiny fraction of the last page of a program might be empty.
Let's dive into Section 3, the virtual memory revolution and demand paging.
This is where the true magic trick happens. The whole reason your modern computer feels so limitless really comes down to a monumental realization in our source text. It is possible for a process to be larger than all of main memory. Lifting this fundamental restriction allowed developers to finally write huge, highly complex programs without ever having to obsess over the strict limits of your computer's actual physical hardware. So how exactly does it pull off this illusion? Well, it operates on something called the principle of locality, which basically assumes a program only ever needs a small chunk of its code at any given second. So the OS only loads the exact pages it needs right now into physical memory. When the program suddenly needs a piece of data that isn't in memory yet, it triggers what's known as a page fault. The OS quickly pauses the process, goes to your hard drive or SSD, grabs the necessary page, swaps it into an empty frame, and then just resumes the program. And the crazy part, all of this happens completely invisibly on the fly.
Now, there is a catch, of course. If your physical memory is totally full, bringing a new page in means kicking an old page out. The OS has to be highly clever about this, using page replacement algorithms like least recently used to try and guess which pages you won't need for a while. If the OS guesses wrong, or if you just have way too many demanding programs open at once, it starts spending all of its time just swapping pages in and out of the disk instead of actually executing any instructions. This dreaded condition is called thrashing. Actually, if you've ever heard your computer's fan spin up like a literal jet engine while your screen just completely freezes, yeah, congratulations, you've experienced thrashing firsthand.
All right, let's wrap things up with Section 4, Hardware Acceleration, under the hood.
Now, you might be thinking, wait, wouldn't constantly checking these massive page tables in main memory to translate addresses effectively double our memory access times? Wouldn't that make everything incredibly slow? And you know what? You'd be absolutely right. To solve this massive speed issue, modern virtual memory uses a translation look-aside buffer, or TLB for short. Think of the TLB as an ultra-fast VIP list. It stores the most recently used page table entries right there on the processor. So when the CPU needs to find a page, it doesn't have to go search the slow, massive directory in main memory. It just checks the VIP list first.
When it's finding a page, the CPU executes this lightning-fast decision tree. Because of that principle of locality we mentioned earlier, most of the time the entry is right there in the TLB. That's a hit. It only goes down the longer, slower route to the full page table in main memory, or worse, triggers a page fault to the disk if there's a miss in the TLB. This one simple hardware addition is literally what drastically improves system performance to speeds we actually find acceptable today.
To really appreciate the sheer scale and sophistication of this invisible process, just take a look at these two setups. We've got the incredibly detailed Intel x86 memory management formats on one side, utilizing optional segmentation right alongside paging for access control. And then we have the ARM memory system overview showing this deeply complex interplay between the CPU, the TLB, the cache, and main memory. These are highly complex hardware ecosystems that silently manage virtual to physical translations millions of times a second. They manage your permissions, privileges, and cache lines, all so you never notice a single second of lag while you're working.
Understanding all of these logistical gymnastics really leaves us with a profound appreciation for that invisible world running right beneath our screens. The operating system, working hand in hand with processor hardware, literally turns finite limits into virtual infinity. It's a true testament to incredible engineering. And I think it begs a pretty exciting question. As our virtual demands continuously outpace our physical hardware, what fundamental computing restriction are we going to lift next? Well, that's it for today. Thanks for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.